seminar from the Instituto de Astrofísica Andalucía. Today we will have a seminar about the PANIC instrument on the Calar Alto Observatory. So part of the PANIC team at the Max Planck Institute in Heidelberg, here at the IAA in Granada, and also in the Calar Alto Observatory, are going to present the update that they have made on the instrument PANIC. So it's been a long-lasting collaboration for several years that now is coming to an end with the opening of the instrument to the scientific community. And in addition to of talking about the PANIC, also we'll have a stellar show by the Minions. I don't know what will be, but we'll see. So there will be several people talking, so Ana Guijarro will be the first one.
Okay. Thanks, Francisco. Thanks, René, that also is just online. Thank you so much for allowing us to present this camera. We are so happy to announce and to inform to all the scientific community the launch of this instrument. We want to give it as much publicity as possible. For this reason, we think that this seminar is the best platform. So thank you so much for this opportunity. I'm Ana Guijarro Roman, so for astronomer in the Calar Alto Observatory. I am going to begin with the presentation. PANIC is not a good name, but we know the next time we are going to use something like a smile, sunrise, but PANIC means that it is a panoramic near-infrared camera for the Calar Alto Observatory, and is the first 4K by 4K infrared camera for the European sky. This is the project team is quite big because, like Francisco said, it's a project so long in time. And the PI of this project is Matilde Fernandez from this house, and also Klaus Meisenheimer, but he's unfortunately passed away. But we are a very big group, and also in the last year, even was a new member like me began to be part of this team just to finish. But don't worry that in this talk we are going to speak only 4 persons of the team, only 4. I am going to give a very brief introduction of the PANIC. Later, Vianak Naranjo from the Max Planck in Germany is going to speak about very brief also about the characterization of the detector. Later, Antonio from the IAA is going to speak about the how to observe with PANIC, how easy it is to observe with PANIC. Later, José Miguel speak about the control and data reduction software, which is very friendly and very, very nice to get a good result with this camera. Is speaking about the quick look, just to have a look of the data just inside, and also for the pipeline, right? And finally, Sara Muñoz, she was here in the institute, but now is in Canarias, is going to give some example of some scientific example, right? The institution that developed this project are the Max Planck Institute in Germany, in Heidelberg in Germany, and also the Institute of Astrophysics Andalucía and the Observatory of Calar Alto. PANIC was designed for the two telescopes, 2.2-meter telescope and 3.5 telescope in the Observatory of Calar Alto. The first light was in 2014 and was operational until 2018 with good result and good performance. But was with a camera of 4 detector, 2K by 2K, and 2 of the detector was suffering some degradation. We decided just to change for a monolithic 4K by 4K camera. For that, in 2018, PANIC came back to Germany from Calar Alto to be upgraded to this camera. Of course, it's not only a change of the camera, it's necessary to make a new design of the mount. It's necessary to adapt in the readout electronic, the software, and that's a kind of job. Finished in 2022 and come back to Calar Alto Observatory, and we began the commissioning, but only in the 2.2 telescope in 2023. With this new detector for 4K by 4K monolithic Hawaii 4RG detector, we have a very big field of view, 26 by 26 arcmin with a pixel size of 50 micrometers, and we are in the near infrared range. That is between 0.8 microns to 2.5 microns. We have for that range 5 broadband filters, the typical ZY, J, H, KS, and 2 narrowband filters, H2 and bracket gamma. This filter, I don't know if that is to do with the arrow. This filter just fit perfectly with the near-infrared atmospheric transmission that we have in the observatory of Calar Alto, right? This is in yellow, right? In yellow we have the transmission, the atmospheric transmission, and you can see all the broad of the filter. PANIC has 4 filter wheels, and we have only 7 filters. For that reason, we offer the opportunity to the community, if somebody are interested to put a new filter. We have 8 empty filter positions, and then it's completely open and free to everybody that is interested in that. For more information, just please check our web page, or also you have the possibility to ask to Conchi Cardana, our project manager, and also the optical engineer, right? And it's just finished my part, and Vianak from the MPIA, is your turn.
Yes. Hi. Thank you, Anna, for the nice introduction. So some of you know me, some of you don't, but well, I'm going to talk to you a little bit about the detector. But in principle, I am going to tell you what you want to hear, everything about the minions. So why a minion? Well, if you paid attention, in Anna's first slide, you see PANIC, and PANIC was by chance made yellow. The first PANIC had nothing to do with the minions. I completely assure you, had nothing to do. With time, when the new detector arrived, we said, oh, it has only one eye, and it is yellow, like the minions. Well, if you know the minions, there are, let's say, more or less 3 different types. A tall one with one eye, a chubby, fatty one with 2 eyes, and a chubby, fatty one with 1 eye. They have names, and the one with the 1 eye and chubby is called Stuart. So our detector is called Stuart. So I introduce you Stuart on the right side of the slides. Well, that's the history. Now to the technical. As you see on the left side, no, please stay on the other slide, Anna. Yes, we have the old detector on the left side with the 4 arrays. They were also, I mean, the coverage was full. The 4K bar 4K was covered also, but we have a gap in between. Right now, we have no gap. You also see from the mount, it is 1-to-1, very similar, that we could reduce as much as impact as possible on any mechanical changes. Unfortunately, the new detector was not compatible with the old mount. So now, yes, please, Anna, next slide. MPIA designed the complete mount. Why not buy it again, like in the first detector? Well, the company was not offering that option anymore. So MPIA said, okay, we will take care of it. Important to mention, I mean, you see this explosive view. We have 2 heaters, loops to control the detector. One on the back, and one exactly attached to the interface plate. it is very important that the interface plate is of the same material as the detector to reduce the thermal impact on it while cooling down, because the detector has a very restricted cool down and warm up rate. And well, everything went fine, and we see our happy steward walking all around, helping us all the way. Now, next slide, please. We also, MPIA was in charge of the readout electronics and the control of the detector. We had to do important modifications on the preamplifiers and the electronics itself. It might seem easier. I mean, we had 4 detectors. Now we only have to control 1. Well, yes, technically yes, but this detector had more channels. And so we have to keep everything under these constraints of having all 64 channels with the same electronics. We were able to handle it with a lot of, test and trial, but our happy steward helped all the way, and we were able to get a signal. Next slide, please. And the last part that MPIA did was the control software of the detector. This is the very low-level software that controls completely all the detector signals. We see here a part of the readout GUI that we use for engineering purposes. Usually an astronomer doesn't use this GUI. The dedicated GUIs will be, and software will be described later, but every single bit of the detector can be controlled with this software. So it was also very important change from our side to be able to handle all the channels and all the new features that this detector may offer. For example, we are able to offer sub-windows, which is very important for the readout times, because having such a large detector implies a certain amount of readout time. In this case, the minimum readout time is 2.9 seconds, which may sound a lot for the infrared, but with the capability of doing the sub-windows, you can reduce the readout times and have almost any combination that you would like to have. And we see, Stuart is very working person, like all minions, and so he gave all his power to have it working. Next slide, please. So the characterization was a very long process, I would have to say. Unfortunately, we had the Corona break in between, and the detector we have to say it is not a super healthy detector. It has a shortcut, but Teledyne was able to work around with it, and we were able to get it to work in the science quality. These are the characteristics of the detector. I'm not going to read them all. You can see from the list. Maybe important to mention that the readout noise is 5.9 electrons, which is much lower than the specs, and we're very happy with the results. Next slide, please. Okay, what happened? What were the, let's say there were 2 major let's say, not so nice things about the detector. The detector is like it is. You cannot choose. And we got this detector. What does it have? It has a reset frame drift. What does that mean? As you see on this slide, the blue dotted line is supposed to be the reset. The reset should not change. Independent of the light coming and on where it ends, the reset should be always like this. Now, next, please. What happens in reality? The reset increases with light or with time. It is, of course, an intrinsic characteristic of the detector that has to be solved in some way, because, next slide, please. The not so nice thing is that it was also pixel-wise, meaning that if you have a saturated star, like you see on with the green curve, the reset was also being influenced from this star, like you see in the middle. I mean, the saturation occurs at about 60,000 counts, and the reset level was increasing from about 11 12,500 to 13,000 at the spot of the saturated star. So after a lot of troubleshooting and testing, next slide, please, we were able to reduce this, now having a almost flat reset in comparison with a saturated star. Now we were able to work. So we're very happy to be able to give this solution and to offer the detector in a safe way to the community. Next slide, please. Also not so nice, but it is almost always everywhere present in all Hawaii detectors is the strong non-linearity. So our detector is almost completely linear from 3,000 counts to a bit less than 30,000 counts. And as you see from the chart, then it deviates. Well, it is a known thing in all Hawaii detectors, and we are working on it. So please, next slide. A fellow of us is working on a non-linearity correction. Results will be for sure not later than May available. And we see that after the correction, we have very low residuals, less than 1%. And you see from different pixels where he picks the as a sample that the results are also similar. I won't get into details, but well, it is a basic, let's say, basic approach. I say like this, not basic, of course, but it is one of the common approaches doing an exponential function and a polynomial correction, in this case of the fifth order, taking residuals for reducing the residuals in this way. Okay, next slide. And well, that was all from my side. If you have more questions regarding the detector, you can contact me offline. Thank you.
Thank you, Vianak.
Well, my turn. I'm Antonio García. I work here at IAA. I'm a software developer, and I have been working in PANIC with this tool, the observation tool, software that gives you the chance to prepare your observation and also to execute the observation at the observatory. This is how a program looks like when you use this tool. In the left side, we have a tree view of all the observing blocks that we can define. And clicking in every element, we can see the information in the right panel. In the bottom, we have a log of every action we are going to take. It is particularly useful when we are running our program at observatory. The main entity we use is observing blocks. Observing blocks are usually related to a target, an object we want to observe. We have the chance to define a single exposure or a set of exposure related with this target. We have different types of observing blocks: calibration series, focus series, dome flat, sky flat, and the default values to get a simple exposure. And we have another element, is the observing sequence for every observing block, in which we have a table with a summarized list of all the exposures that are going to be taken. And in combination with the observing block, we can use iterators and leader pattern in order to prepare more complex observations. This is, well, we have here a button in which we can see the azimuth elevation air mass preview of the target we have selected or we have filled here. And it makes a query to the StartAL tool, Isaac Newton group of telescopes in La Palma, will give us the elevation of the object during the night we have specified. Another kind of observing block is the dome flat. We can select here two types of dome flats. The fixed one, the one in which you select the lamp we want to use and the exposure time, or the calculated, in which the OT calculates the lamp and the exposure time for the given count level you want for this flat. Another kind is the sky flat. This kind of observing blocks is very useful because it takes automatically the sky flat, for dusk or dawn, where the data you have specified in this form. You give this number, and when it's running, the OT is monitoring the sky until we have the image in the range we want, and takes the different number of flat feet we have specified there. And here we have the order in which we have to use the different filter in which we want a sky flat. During dusk in this order, and during dawn in this order. Another kind of OB is the focus series that are very useful during the observation or at the beginning of the night. We have to recalculate the focus of the telescope, and we need to do a series of focus. And then the quick loop is another software that is going to be introduced by my colleague José Miguel later on. Calculates the best focus in this moment, and we send it to the telescope. And the default values is the single information we can provide to take a single exposure. But these default values, we have the chance to combine with dither pattern and iterators that is going to give you the chance of make whatever combination of exposure we want. So we have the dither pattern panel that allows us to prepare whatever pattern we want. And dither is very, very necessary in infrared observation, because we need to mitigate bad pixels, improve sky background subtraction, reduce systematic noise of the detector, and avoid persistent effects or on some pixel of the detector. Here we have a single example of 3 different offsets that we can introduce here. And we also can combine the offset we define with extended object option, in which we move from telescope to sky. The offset we give here in the direction we specify, and then if we click apply, we can see a show preview of what are we going to do. This is a preview of the movement of the telescope. With a number, we have identify the observations in the order they are going to be taken. And in this case, we have a telescope sky extended object, and so we have moving from telescope to sky, from one exposure to the next one. And we have 26.3 arcmins that is the field of view of panic, so we are moving just north in the same field of view of panic. Another example, using 5-point dithering, we have this kind of movement. Another example, combining this 5-point with the extended object, also telescope sky, 30 arc minutes, direction south. We can see the preview of the movement that we are going to take. And this is another way to prepare dithering in the simple way. We only have to specify these 3 fields of integration time, exposure time, the sum of quads, and the total exposure time we want for the whole dither cycle. And one of the predefined patterns that we offer that are 3 different. And then we click apply and get our pattern. Here we have an example of this kind of simple use of dither pattern. And as I mentioned before, we can combine this dither pattern and default values with iterators if we want to make the same observation with the same movement, but in different filters, or changing the number of repetition on every filter, on each filter. So we have here an example in which we iterate by filter and repetitions. 3 filters. 2 of them have 10 repetition, and the other one has only 5. And this panel also allows us to specify the sub-windows that Vianak mentioned before. That allows us to reduce the minimum integration time of the single exposure. Here we have an example of 2 sub-windows that looks like this. And with this definition, we have decreases the minimum integration time to less than the minimum exposure time of the detector, less than the half of the minimum. And when we have our program already defined, we can click in validate and execution if we are at the telescope. Here we obtain 2 tables, one with the list of OBs we have defined, another list with all the exposure, single exposure that are going to be taken. And we have a calculation of how long it's going to last this program to be executed. If we are at telescope, we will have this button available like this, and we are prepared to execute our program. We can choose whatever observer choose the 3 first, or take the down flats, and we have for these three down flats 10 minutes. And clicking run, the observation begins, and the OT interacts.
Now we are back.
We are back?
Yeah.
Yes, you're back.
But you need to put the presentation.
Okay.
Antonio, tienes que repetirlo.
Well, another type of calibration data that is used to have is the dark.
Sorry, Antonio, you're not sharing the screen.
Sorry.
Sharing.
Okay. Okay.
Vuelvo a hacer la cosa de más grandes.
¿Cuál es aquí?
Primera.
¿Esta? Creo, bueno, vamos a ver, no lo sé.
Ahora.
Pero no veis qué es esta. Pero un momento.
No, cualquier cosa.
No es esta la que queremos compartir. No, ¿y por qué no sale? Es que no me deja compartir la pantalla completa.
Dale ahí en pantalla completa, dale a la flechita de abajo, a ver si se ve la pantalla y la puedes seleccionar. Ahí,
¿Esto aquí?
dale. Y selecciona.
Vale, ahí, ahora sí. Gracias, Pedro. Vale, y ahora, sí, pero ahora vamos aquí. Y ahora ya sí.
En modo moderador.
Ahora.
Perfecto.
Okay. Well, I was explaining that at the end of the night, when you have finished your observation, another kind of calibration data that is useful to have is darks. And with this button, we can generate the complete set of dark for all the image that we have taken during the night, and then run and taking during daytime when we have finished the observation. And that's all for my side. There are more info available at PANIC webpage and in the Observing Tool user manual that you can find there. Now it's time for my colleague, José Miguel Ibáñez, to talk about another software.
Thank you very much, Antonio. It's a pleasure for me to be here presenting you the PANIC Second Life. Okay, I'm going to talk about the data reduction of the PANIC data. I will start with overview of the data flow system architecture. As Antonio has already mentioned, the observations are translated to OBs that are ingested into the observation tool, who will send command to the low-level software, GIRS, and also some important metadata that will be very important for the data reduction. It will translate the high-level command to low-level command for the telescope and for the PANIC electronics. Let's say, for example, the readout of the detector or the filter wheels control electronics. This will, as a result, will generate a set of raw data that will be stored in the local system, local file system of the PANIC computer. This data will be saved or stored daily in the morning in the Calar Alto archive. And similarly, during the observation, the quick look will be monitoring all the data that are coming to the local repository in the PANIC computer, looking at 2 new data files. This data file will be displayed in the display. The user can then perform some processing with this data or images that I am going to show you later. The quick look is just a graphical user interface, a sub component of the PANIC pipeline that use, of course, all the receipts and all the subroutines for the data reduction. Well, as you can imagine, the detector upgrade was meaning that the initial PANIC pipeline need to be updated with the new data. Just to point out that with the preliminary detector, we have different detectors, so different calibration for each one, and we have an important issue as well to reduce or to remove the gap between the detectors. Was also an important issue. Now, with the monolithic detector, it's a bit easier to do the data reduction, but it's just to point out that we have a bigger amount of pixels to process simultaneously. Well, because of the intrinsic particularity of the near-infrared observations, what we obtain, because Antonio has already mentioned that the infrared detectors suffer from some particularity of some artifacts like bad pixel, non-linearity, also the near-infrared suffer from the high sky background that need to be, these issues need to be solved. So the observations are planned using the differing pattern and also to splitting the total exposure time into integration time that are divided, the total exposure time is divided into integration time that at the end produce a set or set of raw data that need to be processed to obtain the final image that we want to obtain. Why we need a panic pipeline? Of course, because what from the beginning was our requirement. Nowadays, every instrument needs a pipeline, and we have also an important data volume, and also because of the detector characteristic of the near infrared detector. And another important issue is the sky subtraction because of the leader pattern that we use. Another important issue because of the wide field that we have in our instrument is the distortion correction that we need to apply to the final image. On all this processing need to be automatized and to be put into a software that is able to produce science-ready products. Also, another important point is that for the Commission, it's very important to have some tools that allow you to know if the things are going well. So it's also very important. Well, as I have mentioned, the quick look is just a graphical user interface to have the opportunity to verify whether the observations are proceeding as we expect, and to check that if we need to modify some parameters of the observation. I'm going to show you later some examples. Well, these are the main steps of the panic pipeline. The first of all is to do the data grouping. It means that we need to be sure that we have all the files that belong to a sequence, or a leader sequence, or to a leader pattern to put together in the same data sets. And then the first step of all is to do the non-linearity correction that Vianak has mentioned at the beginning of the talk. Also, another important point is to collapse the queue, because you have the opportunity to save your integration separately, or you can sum up all the integration, depending on what you decide. Then, of course, we need to build the calibration, the master calibration from the different darks and flats, and apply this calibration, darks and flats. Then we proceed to the first sky subtraction that they use a simple median combined using a sigma clip. This is a quick way to estimate the sky background, or the sky model of to subtract to our images. It is done using a sliding window. I mean, we use the closest images to the current one to estimate the sky model. And after that, we have preliminary estimation to remove the crosstalk, because also the detector, the near infrared detector, Hawaii detector in particular, has suffered of some kind of crosstalk. After that, we do the preliminary instrument calibration, and as a result, we obtain a set of frames that are pre-reduced, that are available for a new pipeline that was developed by a former colleague here from IAA, Lemon. It's a differential photometric pipeline. And also, we produce the static image of all the images from for a data set of a same data set that is shown in the quick look display. Secondly, but not for the quick look, we have the science reduction mode that apply a second sky subtraction, taking into account the object that we have obtained with the first quick reduction, with the first sky subtraction, And with this second sky subtraction, we apply again the remove of the crosstalk, because I have not mentioned, but the crosstalk only appears when we apply a preliminary processing of the images. I mean, in the raw data, you cannot see the crosstalk at all. And then, again, we do a astrometric calibration of the new processed image, and again, do a coad or a stack of the set of images. And of course, we can do a preliminary photometric calibration using the 0 point that we have obtained during the commissioning. Well, now just some example of the functionality that we have in the quick look. As I have mentioned before, the data grouping, you can see in the quick look your data sets and what are the files that belong to each one. And as Antonio has already mentioned before, we have to evaluate the focus series in order to know which is the focus that we have to give to the telescope. It's a very detailed procedure in which the user must to select the star, mainly from the center of the detector, to then reject some stars that are not good for the fitting, to obtain a final fitting with the best focus estimation. Here is another example to build the master calibration. You can select during the observation your dome flat, for example, and to create a master calibration. You can also select a sequence and a science sequence to reduce, to do a preliminary reduce to see, because this is a raw image, to see how your field looks like. And if you are obtaining, for example, the signal to noise that you expect or whatever. Also, you can do a preliminary estimated calibration with to the images that you get. And of course, the PANIC pipeline provides you a command line interface to do the processing of your data. Just to finish, the PANIC pipeline is open source and is available in this direction, in this link, and is based on the well-known Python packages that is used by the community. That's all from my side. And now it's a pleasure to give the talk, to give the floor to Sara from Canary Island. Can you, Sara?
Hi, can you hear me?
Yes.
Okay. Hi, everyone. Thank you for coming. I'm Sara, and I have been collaborating with the PANIC team in the scientific area. So today, I'm going to present a sign case for PANIC. But before, I would like to remark as an user of the instrument that the observing tool, PAPI, and the quick look are highly user-friendly and easy to learn and handle tools. Okay, so one of the sign case proposed for PANIC is the study of brown dwarfs. Brown dwarfs are very low mass objects that don't stabilize into the hydrogen burning main sequence because of the lack of mass. So that places them between the giant planets and the smallest stars. As comparison, the figure shows the size and temperature of the Sun, a red dwarf star, 3 different brown dwarfs, and Jupiter. Currently, I'm working in the substellar project at the IAC, and this project is dedicated to study brown dwarfs using Euclid data. So we aim to use PANIC to extend the study to longer and specific wavelengths. Next slide, please. So for this sign case, the main scientific objectives are the detection of brown dwarfs, given that the combination of PANIC with Euclid data will let us to identify cooler objects, performing a photometric characterization, which along with theoretical model will allow us to estimate properties of brown dwarfs, such as their temperature, mass, and age, and the determination of substellar multiplicity by photometric anomalies and propermotion studies. And next slide, please. So PANIC is particularly well suited for this study because of its wide field of view of 26.3 arcmin, which allow us to cover large areas of the sky in its observation. In star-forming regions, its wide field permits the simultaneous identification and analysis of multiple stellar objects, and this provides useful statistical insight into their distribution and properties, and also facilitates precise differential photometry. Next slide. Additionally, PANIC has the proper set of filters to characterize brown dwarfs. The temperature and luminosity of these objects decrease with time, so it is more feasible to detect them in the infrared range while they are young. Here, comparing Euclid gas bands that are the one with the E suffix and PANICs, you can see that the PANIC can provide complementary information to Euclid's observations as it goes farther into the infrared range. And it's also remarkable that PANIC has two narrow filters, useful for detecting emission lines as bracket gamma, that is a potential indicator of accretion luminosity. So we are going to use PANIC to improve our research as we think it's an ideal instrument for this purpose. And next slide, please. But in addition to this time case, PANIC has many other applications in a variety of fields, including extragalactic and galactic astronomy, stellar evolution, star formation, exoplanets, and solar system studies. And thank you, that's all from my side, really quick. I will leave the floor again to Anna.
Yes, thank you, Sara. Just to finish, only to remember that if you want to use PANIC under risky, share risky, it's possible to apply for the next semester from July to December in the observatory, but the deadline is 10th of April. It's only in 9 days, and then just please run to your office and write a nice, wonderful proposal for PANIC. And any question that you have, you can contact with us. Just we can give a tutorial or the thing that you want, right? Okay, thank you very much. I don't know if you have any questions.
Thank you to the whole team. So if you have questions here.
Yeah, thank you very much for the presentation and for bringing this new instrument to the CAHA in general and to our institute in particular. And I've been curious if you have noticed some behavior with the water vapor, because, for example, in the Spectrals project, we have an infrared camera in the south, and we noticed that there are some water vapor fluctuations that are actually mimicking the transit shapes that we are searching for. So I don't know if you have any way to correct
we don't make any big exact characterization about the water vapor. We know that about wall indicator filter. We are still doing some tests, but we don't have any good result to show you about that. But if you want, you can test the next semester. Take your time and you can just test how it's. But it's really that in Calar Alto, what?
Is there in CAHA, because I don't know, but is there in CAHA any water vapor device to measure the water vapor evolution during the night?
No,
because
we don't.
It is impossible to
we don't have any, in the commissioning, we don't have any good data to test that with the water vapor. But we know that Calar Alto is a place that sometimes we have a very big humidity, and we know that this can affect to the infrared, but we don't have that result.
Well, we have, in all the data, we have the weather conditions saved in the headers. Useful for you. All the data have this information in the headers.
Okay, thank you.
Okay. Yeah. Thanks a lot for the different talks, and thanks a lot for the hard work to make this happen. So it's my understanding that you can get images of your source and the sky at the same time using this Windows system.
Yes. And the question is?
Yeah. So this is.
Yes, it's possible to do. The way to observe with PANIC is so easy, just thanks to the work of both of them. and you have a lot of possibility, but it's quite friendly to know about that. You can make dither just if you have a pointing source, you have a smaller dither that is faster. But if you have a standard object, you can make a very big offset that is also quite fast and so easy. It depends on the design that you want to do, but that is completely automatically. Just you choose, like Antonio explained, the dither that you want. Just observe. The good thing is later you can apply this kind of offset that you dither with the pipeline and with a quite good result. Even you can choose with what kind of sky do you want to subtract to the size. Is quite perfect, the pipeline. I don't know if that was the question.
And do you plan to have a narrow band filter for subtraction of the to the H2 and bracket gamma?
You mean to take the science with the broadband filter and to take the sky flat with the...
No, I mean that to get narrow band imaging with, let's say, H2 filter, you usually make a subtraction of the continuum emission using the K band filter. But this has some effect, so it would be better if you have a narrow band filter just close to H2 or in between H2 and bracket gamma so as to make the subtraction of the continuum emission.
We don't make any...
In this case, we have not tested this case, this particular case that you have mentioned. For the observation, it's possible to do this kind of observation with the observation tool. You can define whatever observation you want to, or you need to. But for example, for a pipeline, it's not foreseen this kind of data reduction. It's a general pipeline that obviously not cover all the cases. But from the point of view of the observation, I could say that most of the cases that you can imagine is possible to run to define in the observation tool.
And I think that Conchi or Sara want to say anything? No. Okay. I hear something.
Okay. Any questions? No, online there is question. So if there are no more questions, just let's thank the 5 speakers again.
¿Ya está? Chicas, ¿qué tal?
¿Por qué cerramos?
Oye,